Hello and welcome. My name is Alexander Moreira with AlphaStar Academy, and today we're going to be discussing the problem transforming pairs. In this problem, we want to take the pair AB and turn it into the pair CD using the minimum number of operations. And each operation in this problem involves either increasing the first number by the second number or increasing the second number by the current value of the first number. So let's take a look at an example here. Suppose A was 5 and B was 3, and suppose C was 27 and D was 19. So we want to turn A into 27 and we want to turn B into 19. What we could start off by doing is to increase the first value. So we're going to take the second value and add it to the first value to get 8. And this is one operation. Then we could increase the second value. So we take 8 and add it to 3 to get 11. If we repeat this a second time, we get 8 plus 11 is 19, which is exactly the value we wanted to achieve for B. So we've transformed B into D successfully. And now if we increase the first value, so we take 8 and add it to 19, that gives us 27. And you can see we've recovered the pair CD in 4 operations. And this ends up being the fastest way to do it. So upon seeing a problem like this, a partial credit solution should jump into your mind. And in particular, we want to breadth first search over all operations with a maximum depth of 20. If you implement this, you should receive partial credit. And the pro of this solution is that it's very simple, right? We have 2 operations, we look over all possibilities for how to apply those operations, and we print out our result. The con is that this is extremely slow. So as the sort of depth of operations increases, this becomes exponential and it spirals out of control. So we need a different idea. And the key observation here is that working forwards, so going from A, B to C, D, seems impossibly slow. So what do we do in these situations? Well, we should look and see if there's a solution for going backwards. Can we, instead of going from AB, go to the values, starting from AB and going to CD, can we instead go from CD and go to the values AB? So let's try to consider the problem in reverse. So I have 2 options. I can either decrease the current value of C by 19, or I can decrease the current value of D by 27. Only one of these 2 operations makes sense. Why? 27 minus 19 is 8. That's a perfectly reasonable number. However, if I do 19 minus 27, then I end up with -8. That doesn't make any sense. So the only operation that makes sense here is to take 19 and subtract it away from 27. So I should decrease the first number. And we find ourselves in a similar situation. I could decrease 8 by 19, but that doesn't make any sense. So I have to decrease 19 by 8. So if I decrease the second number, I get 11. Again, it only makes sense to subtract 8 from 11. It doesn't make sense to take 8 and subtract it by 11. So I again subtract 8 from 11 to get 3. And therefore, now that 3 is smaller than 8, I subtract away 3 from 8 to get 5, 3. And you can see that we've recovered A, B. And at every moment, the choice between decreasing the first or second number is forced, as the numbers must remain positive. So what we could do is we could implement a while loop here, which is basically like, if the first number is bigger than the second number, subtract the second number away. If the second number is bigger, subtract the first number away. And this would get you even more partial credit. To get full credit here, anytime you're doing multiple of the same type of operations at once, you just want to do all of those operations in one block, so you don't get stuck subtracting like 1 from a billion over and over and over and run out of time. So the final step here is, if you can decrease a number multiple times, then you should just calculate that factor. and subtract off all of these operations in one go. So let's jump over the code here and see what it looks like. So we're going to, of course, have an operation count. We've got our values A, B, C, and D. And remember, we're going backwards from CD to the values AB. And we're just going to implement a while loop here that continues looping while A is smaller than C and B is smaller than D. As soon as one of the two values falls at or below their sort of target value, we'll handle the rest of the cases separately. So in case one, if C is greater than D, we're going to reduce C by multiples of D until it's true that C is at most D. So if C is greater than D, we're going to define X to be C minus 1 divided by D. This is basically just telling me how many copies of D fit into the value C. So then I'm going to use X operations. So I'll increase my operation count by X, and I'll subtract away from C D times X. So this is the maximum multiple of D that I can subtract from C while maintaining a positive value for C. And then I can repeat this sort of symmetric case for if D is greater than C. Again, I calculate this value X, I add X to my operation count, and then I subtract off the biggest multiple of C I can from D. If you do it one factor of C at a time or one factor of D at a time, you'll get sort of half the cases, but you'll time out on some of the larger test cases if there's a lot of operations where we have to do the same operation over and over, like in the second sample test case. And then if it's true that C is equal to D, then we should just break out of the loop. We can't make any more progress at this point. So then there's just a couple cases to check. If B is equal to D, then we want to check, can we use one last sort of series of operations to transform C into A? And to do that, we can just check if B is equal to D and C is at least A, does D divide the difference between them? If that's true, then we'll just print out operations plus the number of times that D fits into the current difference between C and A. And then there's the symmetric case for if A is equal to C. So if A is already equal to C, we check, can we reduce D down to B? If we can, we return that operation count. And then if neither of those are possible, we simply return -1. So that completes the program here. Thanks so much for watching the videos, and I'll see you in the next one. Bye bye.